In this video, we will be discussing controlling plasma in jet and looking towards the future of fusion reactors. Now this involves some incredible physics. Let's see what happens when we drop a magnet down a copper pipe.
When you drop a magnet down a copper pipe, it will fall down really slowly.
So when you drop a magnet, you are creating a moving magnetic field because the magnet has a magnetic field already, and when it's falling, it's now moving. And when this moves past the free electrons in the copper pipe, it induces a current in those electrons. So the moving magnetic field then produces a swirling current of electrons inside this copper pipe. It's called an electrical eddy. And these eddy currents produce their own magnetic field, and this magnetic field is in opposition to the magnetic field of the magnet. That means the magnet is slowed down as it falls.
But how is this relevant to controlling plasma in jet?
So plasmas are incredibly hot. They cause a lot of damage to just about anything they come into contact with. The plasmas in jet are incredibly stupidly hot. They are hotter than the sun, so they will cause significant harm to any components that they do touch.
We can prevent the plasma hitting the wall using a magnetic field. To demonstrate this, we did an experiment. The blue electron beam represents the plasma. As the electron beam passes through the magnetic field, it bends. So this means that plasma can be controlled because it was deflected. The electron beam shows how the plasma in the Phys reactor can be controlled by a magnet.
So the magnetic fields in jet are very carefully designed to make the plasma flow in a certain direction. So as the electrically charged parts of a plasma, the ions and the electrons, try and cross magnetic field lines, there's a force exerted on them. And the magnetic fields themselves are constructed so that no matter how they try and move, no matter how the plasma tries to move, it's always directed in a certain way.
JET is a research fusion reactor that uses magnetic fields to control plasma.
So in jet, there are very specifically designed magnetic fields. So jet is a magnetic confinement nuclear fusion device. That means it uses these magnetic fields in a very specific arrangement to keep the plasma away from the walls and keep it flowing in a certain way.
The jet experiment consists of several different components. There's a huge amount of engineering infrastructure that goes into running a plasma pulse. So the process that I work in is the active gas handling system. So this is a small, almost like a factory, that makes and processes and stores and purifies deuterium and tritium and hydrogen. So that's one part. You then have the torus hall, which is where the jet reactor sits. So this is the fusion reactor and all the diagnostics. So these are special instruments that they can use to monitor what's going on inside. You have a cryo plant. So this is where you store all your cryogens that you use to keep everything cold. You have a huge amount of pumping facilities. And then it takes a huge amount of electricity to start up a plasma pulse, and that's more electricity than we can draw from the national grid at one time. So there's a huge amount of engineering infrastructure called power supplies.
JET is a good demonstration of a nuclear fusion reactor. However, it consumes more energy than it produces.
We will be fueling the reactor with deuterium and tritium in the next experiment, which means we get much more powerful plasmas and much more energy released in the fusion experiments. And that's getting ready for the scaled up reactor that they're currently building in France, which is ITER, which will be a bigger fusion reactor. One of the big technical challenges that the fusion research community still have to solve is how, or what is the best way to get the energy from the plasma out. And at the moment, it looks like we'll do that by having the neutrons that come out of the plasma hit a kind of blanket around the reactor. They call them breeder blankets, and these are devices that will take the neutrons and turn them into more tritium for future fusion fueling, and then also transfer the heat from those neutrons into a heat transfer fluid. So that's something that will take the heat and move it to somewhere else, and then we'll use that heat transfer fluid to raise steam and then generate electricity. I don't think in the near future. I'm optimistic that we might see the first demonstration fusion power plants within my lifetime.
3, 2, 1.